Welcome back to the classroom. My name is Mr. Wong. Today we'll be explaining the 2020 independent physics paper, question 30. And this question aligns with module 7, inquiry question 3. Or 2 actually. In this question we have the photograph below shows two lenses of a pair of glasses in front of the same light source. The arm of the glasses is pivoted on the left hand side so that the angle of the arm relative to the light source can be changed. So this point here, I might just do it in a different color. Doesn't really help. Highlighter. Okay. The photograph shows two lenses at 4 different positions. So we have this lens here and this lens here. We're going to do a label just so later on in the question we can reference them. So we'll call this lens 1, 1, 1, 1, and this is lens 2, 2, 2, and 2. Okay, in terms of principles of physics, we are going to start doing a little bit of underlining. So we are going to look at the principles of physics. Account for the lack of change in the light passing through the left lens. So the concept we need to cover is the lack of change of light passing through our left lens, and compare that to the changing amount of light passing through the right lens. And the main point is as the inclination angle is increased. So what you can tell from this image here, we can already see that this concept is about polarization. Okay, so we want to explain what's happening in terms of polarization. Let's firstly start with the first lens. Okay, so lens 1. So a lack of change in brightness is due to the lens having no polarizing filter. Okay, so that's what we have there. We also know that lens 2, it is fading because of there is a polarizer. So lens 2, brightness decreases due to the lens being a polarizer, or you could say another way of saying that is having a polarizing material in it. Okay, so that's doing our first comparison. The next comparison we're going to be doing is implementing some physics principles. And this goes back to Malus's law. So according to Malus's law, which says I of the I max of whatever material we're looking at of the original intensity is cos squared theta of the angle. Okay, so max that as lens 2 is rotated towards 90 degrees, as cos squared 90 is equal to 0, the brightness of lens 2 becomes 0. Okay? There's another implication though that we can identify. So as lens 2 becomes completely dark, remember the only way a polarizer can ensure that no light is transferred through must imply that whatever screen that was in front of them, being this screen here, is also a polarizing material. So we already had a 50% reduction in terms of the brightness before it reached our polarizer here. Okay? Otherwise, we would see a decrease, we would see a 50% decrease, but we shouldn't see a reduction like this. Okay? So as the lens 2 becomes completely dark, this implies the screen in front was also a polarizing material. Okay, so the kind of equation we're getting here is e.g. the intensity of screen 2 is equal to the intensity of the screen, cos squared theta, which we can rewrite as screen was 50%, cos squared 90, that leads to 0 either way. Okay, so there's that, it's polarizing material. We can also even label, I didn't mention it before, but this is screen 2 is an analyzer. So that's for our second polarizer, while as our polarizing screen is our first polarizer. And so that explains why we get a reduction in the brightness because of Lenz's law, because we are taking it to 90 degrees, but also because there is there was a first polarizer where light traveled through before it went to lens 2. And the reason why lens 1 doesn't see any change in polarization is because it's not made of any polarizing material. Okay, so that's our response. I'll leave it there. Thank you so much for listening. I am Mr. Wong, so thank you for joining and hope you all have a nice day after listening to this explained video.